Okay, we are on 6.2, the chemistry of buffers. This is for AP Chem, and I'm going to share my screen. We're on page 362, but we're going to skip this warm-up, and we're going to look down here at the bottom of the page under the definition of a buffer. So an acid-base buffer is a solution that resists changes in pH after you add a small amount of a strong acid or a strong base. Okay, and let's take a look at the next page where it talks about the components of a buffer. So the components of a buffer are a weak acid and its conjugate weak base. Now, there are things called acidic buffers. What that means is it's a buffer solution that will work in the acidic region of the pH scale. Okay, let's go ahead and turn the page. So since we're working with a weak acid, for instance, you can write a Ka for something like that, right? And then you can rearrange that to solve for the hydronium ion concentration. So when you've got a weak acid, you can actually solve for the hydronium ion concentration if you're given the Ka and the concentration of the weak acid over the concentration of the conjugate weak base. So this is a really, really important equation. So what this tells us is that the hydronium ion concentration and the pH, really, of a buffer solution depends on two things: the Ka of the weak acid and the ratio of the concentration of the weak acid to its conjugate base that's in that specific solution that you're looking at. Now, when the ratio is a value of 1, what that means is the hydronium ion concentration in the buffer is equal to the Ka of that weak acid. If the ratio increases, the hydronium ion concentration increases. And if the ratio decreases, the hydronium ion concentration decreases. Now, if we dilute the buffer, the concentrations of the weak acid and its conjugate base are reduced equally, and the ratio will remain constant. This means that the hydronium ion concentration and the pH does not change when a buffer solution is diluted. Okay, so let's take a look at the quick check. It says, why do we normally attempt to make the concentrations of the weak acid and its conjugate base in a buffer solution approximately equal? Well, this is because it will allow the buffer to resist changes to its pH equally following the addition of small amounts of strong acid and strong base. Number 2, in a buffer that contains Ha and A negative, the conjugate base A negative will react to neutralize any acid that's been added. As a result, the addition of a small amount of a strong acid to a buffer solution will make the ratio increase and the hydronium ion concentration will increase and the pH will decrease. Now, number 3 asks us to circle the pairs of species that could be used to prepare a buffer solution. Remember, we need to have a weak acid plus its conjugate base. What this means is the weak acid and the conjugate base will contain the same anion. They will differ by a hydrogen ion. So HNO3 is a strong acid, so that's out. It's there and there. We don't have an acid here in either one of these pairs. Hydrochloric acid, strong acid, so it's out. Here I have hydrofluoric acid, which is a weak acid, and I have KF. And I'm going to go ahead and highlight so they stand out to you the fact that we have the same anions. Okay, so therefore this would work. Now over here, I've got the CHOO anion, and this would be a weak acid here if you look at your Ka table. So I would circle that because they both contain the same anions. Then if you look at the table, you'll also see that here we have the same anions. Here we have the same anions. They differ by one hydrogen. But you'll see that this substance and this substance are listed in the Ka table as weak acids. So therefore, I can circle both of these because they both contain the same anion and they differ by one hydrogen. Okay. Now, let's talk about pH change resistance after the addition of a strong acid to an acidic buffer. So when you add a small amount, let me move this book for a second. Okay, that's better. When we add a small amount of a strong acid to a buffer, the conjugate base will react with those hydronium ions from the acid. And you can see that down here. So here what they've done is they've taken a conjugate base of something, and the hydronium ions are going to combine with the conjugate base, and we're going to produce this weak acid, which is acetic acid, and water. So a hydrogen is going to be given to that conjugate base. So we're converting to the weak acid. Okay, so that would cause the weak acid concentration to come up and this conjugate base concentration to go down. Okay, on the next page, it says that all of the hydronium ions from the strong acid are converted to the weak acid and water in the reaction, which causes the weak acid concentration to increase and the conjugate base concentration to decrease. So the buffer component ratio increases and the overall hydronium ion concentration is going to increase, but by a very, very small amount. Okay. Okay, let's go on to the next section on pH change resistance after the addition of a strong base to a buffer solution. Okay, so for here, when a small amount of a strong base is added to a buffer, the weak acid reacts with the hydroxide ions from the base. So here we've got our hydroxides reacting with this weak acid. Just gonna make a note here. Here's my weak acid. And a hydrogen is going to be given to the hydroxide, and you're going to form the conjugate base, which is the acetate ion, and water. So the conjugate base concentration is going to increase, and that weak acid concentration is going to decrease as all of this hydroxide is converted to conjugate base and water. So down here it says all the hydroxide ions from the strong base are converted to the conjugate base of the weak acid and water. This decreases that weak acid concentration, increases the conjugate base concentration, and the result is the buffer component ratio decreases, so we decrease the overall hydronium ion concentration, but only by a very small amount. Okay, now, if you take a look at the next page here. They've given you a summary right here of everything that we just discussed. So if you have a buffer solution and you added some concentration of hydroxide, the hydronium ion concentration falls and the pH rises just slightly. In the middle here, this is showing you when you have equal concentrations of acid and conjugate base, how the concentrations of the weak acid and the conjugate base are equal. Over here, this is showing you after you add some concentration of hydronium ions, the hydronium ion concentration rises and the pH falls just slightly. So these are the effects on pH after adding a strong base or a strong acid to an acidic buffer. Okay? If you take a look at the practice problems on the next page. So here in practice problem number 1, it says fill in the blanks in the statement below. Following the addition of a small amount of strong base to a buffer solution, the HA over A minus ratio is going to decrease. The hydronium ion concentration will decrease slightly, and the pH will increase slightly. Part B, write the net ionic equation for the reaction occurring when a small amount of NaOH is added to the buffer solution discussed in the sample problem up above. So what we're doing is we're going to be adding, let's take nitric acid, and I think they forgot to put nitric acid somewhere up here because it's mentioned down here in part C. So that's kind of where I'm getting that from. So nitric acid is going to have some hydroxide ions. And what's going to happen is a hydrogen is going to be given to the hydroxide. And that's how we get this NO2 negative 1 and H3O plus 1. Okay. How will the nitric acid to NO2 negative 1 ratio, the hydronium ion concentration, and the pH change after we add a strong base? Well, the HNO2 over NO2 negative 1 concentration, this ratio is going to decrease. Okay. Which makes sense because if this gets larger and this is getting smaller, the overall ratio decreases. And the H3O plus concentration decreases slightly and the pH increases slightly. Okay. And then let's take a look at question number 3. Determine if each of the following solutions qualifies as a buffer. Briefly explain your answer in each case. Let's just take a look at A. So here we've got 0.1 molar HI and 0.1 molar NaI. Well, I negative 1, I would say no here. And that's because I negative 1 is the conjugate base of a strong acid. So it can't accept a hydrogen ion and neutralize added acid. Okay, because if you look back at the table, I don't have that, I should have that table earmarked in my book, but I don't. But if you look back at the table, I think it's page 289, HI is one of those top 6 strong acids. So that means you've got a one-way arrow. There's no equilibrium arrow there. Okay, let's take a look at the next page. Okay, on page 368, buffering a solution in the basic pH region. So here, a solution that buffers in the basic region on the pH scale is called a basic buffer. And you can write a Kb expression for a weak base, which means you can subsequently solve for the hydroxide ion concentration if you rearrange it. And you're going to get a really important equation that looks like this. So the hydroxide ion concentration and the pH of this kind of a buffer solution depends on two things, the Kb of the weak base and the ratio of the weak base to its conjugate acid that's in that solution. So what this means is if the ratio increases, the hydroxide ion concentration increases. If the ratio decreases, the hydroxide ion concentration will also decrease. Let's take a look at the bottom of the page. pH change, resistance after the addition of a strong acid. Okay, so when a small amount of a strong acid is added, the weak base reacts with the hydronium ions that are in the acid. So here you've got your weak base ammonia. Okay, and you're going to have a hydrogen donated to it, and you're going to form its conjugate acid. So what happens is all of the hydronium ions from the strong acid are going to be converted to the conjugate acid of the weak base and water. So this is going to increase the ammonium ion concentration and decrease the ammonia ion concentration. And the result is that the buffer component ratio decreases, which decreases the overall hydroxide ion concentration, but by a very small amount. And that's how it buffers. So if you take a look at page 351, at pH change resistance after the addition of a strong base. Over here, when a small amount of strong base is added, the weak conjugate acid reacts with the hydroxide ions from the base. So here is your weak conjugate acid. And you're going to have a hydrogen being donated to the hydroxide, and then you're going to end up forming an H3. So what happens here is that all of the hydroxide ions from the strong base will be converted to the weak base and water. This will increase the ammonium concentration and decrease the ammonium ion concentration. The result is, as the ratio increases, the overall hydroxide ion concentration will increase by a very small amount. Okay, let's take a look at the next page. They've given us a summary of all of this. So at the top of page 370, this is the summary of the effects on pH of adding a strong base or strong acid to a basic buffer. So here's your original buffer solution with equal concentrations of acid and conjugate base. On the left side, after you add hydroxide ions, the hydronium ion falls and the pH rises slightly. On the right, after you add hydronium ions, the hydronium ion concentration rises and the pH falls slightly. Let's take a look at the practice problems at the bottom of the page. So here it says, each of the following solutions contains a weak base. What compounds would make each a buffer solution? And they want to know what concentration ideally would do that. So if you've got a 1 molar CH3NH2, you're going to lose one of these. You're going to gain, you want to gain a hydrogen. So you want the concentration to be the same. And then what you would do is you would add a hydrogen, but then you would add some sort of substance that is going to get rid of the charge so that it's neutral. So what you did was, if you go ahead and you add a hydrogen to here, you're going to get a +1. So I would go ahead and I would add some sort of a halogen with a -1 charge to make this neutral. And that's what I did here. Okay. Over here, N2H4, make the concentration the same, 0.80 molar. And then you've got to add a hydrogen to this. So that's going to give you N2H5 plus 1. So what I would do is I would go ahead and add some sort of component to make that N2H5 plus 1 neutral. So I would add something with a -1 charge. You could add a nitrate ion because nitrate has a -1 charge, and that would make it a neutral compound if you wanted to. Now here, you would take the same concentration, and then what you're going to do is you're going to add a hydrogen to here. So you could make this CH3 to NH2. Remember, that's a +1, but we need to make it neutral. So I'm going to go ahead and add a halogen onto the end there. So this would normally be NH2 plus 1. And if I add a halogen with a -1 charge, it will make that a neutral compound. Okay. Now, take a look at number 2. Number 2 says, write the 6 net ionic equations representing the reactions occurring when a small amount of strong acid and small amount of strong base are added to a basic buffer solution. Okay, so if I'm going to use this substance here, and I've got my hydronium ions, what's going to happen is you're going to have a hydrogen given to that substance, and that's how we form our CH3, NH3 plus 1, and then just neutral water. Now, if we're going to do it with a base, what I'm going to do is I'm going to take the CH3, NH3 plus 1 substance, and here's your hydroxide ions from your base, and then what's going to happen is you're going to end up donating a hydrogen to the hydroxide so that you get CH3, NH2, and then your neutral water, like that. Okay. Now, if we go to the next page, let's talk about the Henderson-Hasselbalch equation. If you generalize the ratio for any conjugate acid-base pair, we get this equation called the Henderson-Hasselbalch. So the pH is equal to the pKa plus the log of the concentration of the base over the acid. This is a tool for analyzing and preparing buffer solutions. Okay. Now, move on to buffer capacity. Buffer capacity is the amount of acid or base a buffer can neutralize before its pH changes significantly. So a more concentrated or high capacity buffer will experience less of a pH change following the addition of a given amount of strong acid or a strong base than is less concentrated or low capacity buffer will. Okay. Okay. Now, let's go to the next page for preparation of a buffer. Right here, it says that a buffer is effective only if the following condition is met. The ratio of the anion to the weak acid or the conjugate base over the weak acid has to fall within this range. So when we prepare a buffer, we want to find a weak acid whose pKa is as close as possible to the desired pH so that that ratio will fall within our desired range and be as close to 1 as possible. Okay. Now, let's talk a little bit more on the preparation of a buffer. A buffer is most effective when the component concentration ratio is closest to 1. The best weak acid will be the one whose pKa is closest to the target pH value. That's what was said up above. Higher concentrations make better buffers. That means that low concentrations are typically avoided. So typically what you want to do is have concentrations between 0.05 and 0.0 molar when you're making a buffer solution. Okay, let's go on to page 373. So here they want us to rank the following solutions in order from the lowest to the highest capacity. Okay, so if you look at the concentrations, and let's see here, we've got 0.48 molar and 0.5 molar, 1 to 1, 0.1 to 0.095, 0.04 to 0.06. So this 1 molar being the highest concentration, I would say that that has the greatest capacity. Lowest capacity, I would say, is this 0.04 and 0.06 concentration. And then everything should fall in between. D should go here, and A should go here because of the ratio. This is a 0.095, and these are both at 0.4 and 0.5, which are really close to each other and much larger than that. We're going to skip number 2, and we're going to go to number 3. Prior to being used to measure the pH of a solution, pH meters are often calibrated with solutions buffered to a pH of 7. Also, a pH of 4 and 10. Use the table of relative strengths of acids and bases and the Henderson-Hasselbalch equation to select 3 appropriate conjugate acid-base pairs that could be used to prepare these buffer solutions and complete the table below. If you take a look back at the table, benzoic acid actually has a pKa value of 4.19. And benzoic acid is C6H5COOH. So if you remove one of those hydrogens, like the one on the end, and you put, let's say, a alkali metal with it to neutralize it, to make it have a 0 charge, you would get something that looks like that for its conjugate base. You could have put a different alkali metal with it. You could have put lithium or potassium. It would have been fine. Here, if your desired pH is 7.00, well, the bisulfite, or bisulfite ion rather, has a pKa of 7. So that means that you're going to be using the HSO3 -1 ion. So if I put another alkali metal with that, like sodium, I'm going to get NaH. Actually, I'm going to lose that H. So it's NaSO, Na2SO3. Here, if I'm at a 10, if you look at the table, phenol is going to have a 9.89 pKa value. And that means that it is C6H5OH, I believe, for its formula. So if I lose that hydrogen on the end and I put an alkali metal with it, like sodium, I'm going to get that salt for its conjugate base. Okay. Okay. Now we have one last thing to talk about, and that's the maintenance of blood pH. So let's come down here. The 2 most important functions of your blood are to transport oxygen and nutrients to your body, and they also are going to remove carbon dioxide and waste from them. So hemoglobin transports oxygen in your blood, and that is represented by HHB. This is actually a weak monoprotic acid. So here it is here in this equation. So what's happening is if the hydronium ion concentration is too low, then equilibrium is going to shift to the far right. And that means that this concentration is too high to allow for the adequate release of oxygen. If the hydronium ion concentration is too high, then the equilibrium shifts to the far left, and then that HbO2 -1 concentration is too low. And as a result, hemoglobin's affinity for oxygen is reduced and the molecules won't bind together. This is known as acidosis. Okay. If you turn to the next page, let's take a look at the quick check here. It says, write the net ionic equation representing the result of adding hydronium ions to a solution containing this buffer system here. Well, if you have your HPO4 -2 plus hydronium ions, what will happen is this is going to give a hydrogen away to form H2PO4 -1 and H2O. And B, if you're adding hydroxide ions, then what will happen is the hydrogen will be given to the hydroxide. You'll form HPO4 -1 and H2O. For question number 2, people under severe stress will sometimes hyperventilate, and that can lower the carbon dioxide concentration in blood so that you pass out. So if we're talking about the equilibrium and the effect of hyperventilating on blood pH, if the concentration of your dissolved CO2 is too low, the equilibrium shifts left and the hydronium ion concentration drops, which raises the blood pH level, okay? Why might breathing into a paper bag reduce the effects of hyperventilation? Well, that means your exhaled breath containing carbon dioxide is re-inhaled. And this is going to raise the concentration of dissolved carbon dioxide in the blood, which shifts the equilibrium to the right, and the hydronium ion concentration in the blood increases, and the pH lowers.